Hi, everyone. My name is Brandon Rodriguez from the Jet Propulsion Lab at NASA's JPL in California. Thanks so much for joining us today. As you can see, I'm not truly at JPL as we still wrestle with the pandemic. So we're working from home, but that doesn't mean we can't bring you guys some exciting science and all the latest happenings out of JPL. Because we're working in these crazy times, really what we're excited about in the education department at JPL is bringing you guys a little bit of a kind of a new flavor to some of these workshops. Maybe before the really exciting Perseverance launch that you saw back in July, you subscribed to a few of these and tuned in to our 3 workshops. This is the 4th in that series, but we're going to switch things up a little bit by pairing this up with a second opportunity. That will be on Saturdays for educators, specifically for K-12 teachers, or if you're teaching from home or you're part of a camp or something like this. We want to be able to give you guys the opportunity as we get back to school to take all of the great things that we're going to discuss in our Wednesday sessions and kind of translate that into opportunities for you and your kids and your students so we can really have some engaging science in the classroom. Even if you're not technically in the classroom. So we'll discuss a little bit about that towards the end, where we'll highlight what it is the education department at JPL does, our offerings, and how we can hopefully help you. But for today, we want to kind of just explore NASA in general. And in our 4th session here, we're going to talk a little bit about the future of Mars exploration. So again, if you were dialing into some of our previous sessions, we talked a little bit about Perseverance, just a general overview. We focused one time on just engineering, another time just on science. And today we have an awesome speaker, a good friend of mine, Leonard Ortiz, who is going to talk to us about not just some of those, the highlights and capabilities, but the future of Mars exploration. What can we really look forward to next? If you registered for the Q&A section, I have that open, and we'll get a chance to get some Q&A afterwards so that we can kind of, further explore some of these really cool new features of the Perseverance rover and our future plans in Mars research. But first, let's turn it over to my colleague. Leonard is a great ally to the education office. I actually met him when he came in and asked how he could help, which as an educator was the greatest sensation to ever hear, because so many scientists and engineers think that they can walk into a classroom and they say, I'm a scientist, how hard can it be to teach a class of 8th graders? Turns out pretty hard. So he's been such a great friend to the education department. We're really lucky to have him. So let me turn it over to Leonard.
Oh, thanks, Brandon. Thanks for that introduction. Hi, everyone. My name is Leonard Ortiz. I'm a manufacturing engineer at NASA's Jet Propulsion Laboratory. And today I want to talk to you about a little bit about what I do at JPL, as well as an overview of the Perseverance rover mission. And we'll take a look at the differences of Curiosity and some of the new instruments that we have going on Perseverance. So as a manufacturing engineer, I get to support the fabrication, beginning to end process of flight hardware, as well as non-flight hardware. So what does that mean exactly, right? Well, I help build parts for space and also for testing here on the ground, something we call mechanical ground support equipment, which is MGSC. So on the first slide, we have a video that I'll be showing you that we can see all the small little parts and components that go into building not just the rover, but the crew stage itself. And so all these parts have to be qualified and have to go through an inspection process. And it's actually a pretty long process to get something to be certified to fly. So the Perseverance rover has actually undergone quite some time being tested and built and assembled and all the crazy things that go on. But the best thing about my job, I think, is being able to work with some of the amazing machinists, the technicians, the people behind the scenes, and some that you can see right here in front of the scenes in the bunny suits at JPL, working at the spacecraft assembly facility, which we call the clean room. So as you can see, there's a lot of like components that go into building a spacecraft. And so getting things to fly is not easy. It's a task that undergoes a lot of testing. And that's one of the things at JPL that we do, test, test, test. And so since I've started at JPL back in 2018, I've had the opportunity to work on the Perseverance rover on the MGSC side. So I helped with some of the configurations of the centrifuge test, as well as the surrogate rover that we use for testing and alignment of the cruise stage stackup. So that's kind of a little bit about me. But for the most of the presentation, we'll be talking about the Perseverance rover and what is new and some of the similarities between that and Curiosity. So if you go to slide 2, we can see here that we didn't just build the rover just now. We've had a long running of building Mars rovers for a few decades now. So actually, we started with the what we call the Pathfinder mission, which was one of the first rovers to rove on Mars back in 1997. That one was a tech demonstration to see if we can actually communicate with something that's moving on Mars, as well as travel and rove on the surface of Mars. And then from there, we now have the kind of Perseverance rover, right? But it took some time to get to this point. The Mars exploration rovers, the Spirit and Opportunity, those were our main bread and butter of the engineering behind these rovers, right? We had the tools, we had the wheels, and so what we call the rocker bogie system, which now we've used so many times that we are able to rove safely on the surface of Mars. And but Spirit Opportunity, as you can see, they use solar panels, right? And so the Curiosity rover, once we built that, we iterated those the energy system to be able to use the what we call the MMRTG, which is the multi-mission radioisotope thermal thermoelectric generator. And so with the MMRTG, we're able to use what we call a nuclear power to power the rover, convert the energy into heat, and keep the rover fully functioning. And then from the Curiosity rover using that, we went and used that same system into the Perseverance rover to be able to power that. And so if you go to slide 3, here we can see the mission timeline, right? We just launched on July 30th, a few weeks ago, and we are on our way to Mars. We will be landing on February 18th, 2021. And so that's going to be a really exciting time. We will be going through our EDL stage, which is the entry, descent, landing, which if you haven't seen the Curiosity 7 Minutes of Terror, I suggest you look that up. It's really, really terrifying how we land on the surface of Mars now with a 1-ton rover. But that's something that we'll be repeating, right? And so, but you might be asking, why are we going to Mars? Don't we already have a rover there? We do, right? But Curiosity wasn't made to actually look for ancient past life. It was there to study the geology and see if Mars was once habitable, right? But Perseverance is actually going to be looking for microbial life, biosignatures of ancient life, and to finally put to rest is to find out if we are alone. And that's a very, very, very scary question, but something that we're excited to do and find out. So we'll be landing at Jezero Crater. If you look at slide 4, this is an ancient delta, which we once thought to have a body of water. So where we'll be landing is where the inflow water is. And there's actually, the crater has inflow and outflow. So we believe at one point this crater was full of water. And so we'll be going there to see and study the soils and the rocks to see if it once contained life. So some of the new instruments on the Perseverance rover are not like the Curiosity rover. If you go to slide 7, we can see a side-by-side comparison of Curiosity and Perseverance. And at first you might be thinking, well, these rovers look exactly identical. Yeah, they kind of do. The chassis and the body, the full frame of the rover is pretty much identical, something that we didn't really want to redesign and go through the whole process again. But if you look closely, especially at the wheels and some of the the instruments on the arm, you can see some of the differences, right? So if you look at the wheels on slide 8, this is where we can see the main difference of the Curiosity rovers, just like from afar. So the wheels, we actually increased the diameter by about 0.7 inches. We narrowed it down a little bit, and then we redesigned the treads on these. The treads before on Curiosity, these are called the chevron design, right? And the chevron design has kind of like a zigzag pointed edge tread, which over time, if you haven't heard, this caused some harm, and it caused some cracking right in the middle of the wheel. So we went back to the drawing board. We went through iterations of designs using 3D printing as well to figure out what size thread, what size, what length, what thickness, and what design would be most optimal for the new wheels. So we ended up with the new wheel that you see on your right. And so with this wheel, we tested in what we call the Mars yard at JPL. And so at the Mars yard, we went through so many different tests to see if this wheel would actually endure. And yeah, we tested, and we saw that it did endure, and it's now on its way to Mars. So it's really, really exciting to see something like this, going from something like a design that we've used in the past, but redesign, reiterate. And that's kind of what engineering is, right? We focus on trying to see what is most efficient and most optimal, but then we see that there's a little bit of failures, but along the way, we figure out how to make things better. And failure sometimes is an option, but we pick back up and we redesign and we optimize. So something that I do for my job is that as a manufacturing engineer, we get to focus on the kind of like the machining part of the components, right? So if you look at the clip, at the first clip, you can see some of this machining happening, right? There is a little portion where you could see. So what we do is we take a huge block of metal, and a huge block of metal, we go through a concept called subtractive manufacturing. And subtractive manufacturing is, taking this chunk of metal, cutting it into the design that we most desire, for, in this case, is the wheel. And so taking that chunk of metal, getting to where we want, is something we also call build to print, right? So we get a blueprint, and with GD&T, which is geometric dimensioning and tolerancing, we are able to work with designers, project engineers, and be able to make these parts come to life. And that's kind of like one of the most rewarding parts of my job, I believe, is being able to see something go from paper to an actual physical object. And it's kind of crazy to think about. But yeah, that's kind of something that I get to do in my daily activities, see things come to life. Now we're going to go back to talking about the perseverance and curiosity differences, right? We go to slide 9, we can see that some of the new instruments on the rover are on the turret. We also have 23 cameras versus Curiosity had 17 cameras. And one of the coolest ones and coolest systems on this Perseverance rover that will pave the way for future human exploration and robotic exploration is the sample caching system. And that's what I'm most excited to talk to you about, but we're gonna have to wait a little bit. First, we're gonna go through some of the cameras on this system. So if you go to slide 10, you can see the two of the main instruments on board, Sherlock and Pixel. These two will actually be the two that will be most vital to finding signs of ancient life, right? And then if you go to slide 17, here we can see exactly what Sherlock and Pixel are going to try to find, right? So Sherlock is going to be looking for carbon-based minerals and organic molecules, while Pixel is going to be using X-ray spectrometer to find composites of elements, and it's actually rated to find over 20 chemical elements. So with these two instruments combined, we'll be able to find and see if Mars had at one point life. And so what we're looking for is actually microbial life. And so Sherlock is the instrument that, as you can see in the above image, Sherlock is looking for those biosignatures and kind of like the fingerprints of Mars. So by looking for the fingerprint, you can see and date back to at which point, if there was or is life there on the surface of Mars. So now if you go back to the Perseverance rover cameras, slide 10, you can see also some of the new instruments on board, like the cameras, right? So the cameras are actually some of the coolest cameras that we're going to have on the surface of Mars. These are actually rated now to 20 megapixels. And we actually have a video camera that we'll be using when landing on the surface of Mars, which is going to be super crazy because we're actually going to be able to take video of us landing and seeing exactly how this all works, because we've had images before from Curiosity, but this time we're actually going to be able to see in full definition of this whole EDL process. So if you go to slide 11, here you can see where the camera is going to be at. So from when we enter the atmosphere at 13,000 miles per hour, and once the heat shield pops off, the rover will start recording, and we'll be able to see frame by frame how the whole EDL process is. And that's something really to look forward to, because before, it was just still images, and we have the computer generated video that we have, which will also be soon, which will also be coming soon with the Perseverance rover. But with the video, it's going to be so much better. And so with the if you go back to the cameras, slide 10, we could also see we have a couple other cameras. The front has cameras, the rear has cameras. These will help Perseverance kind of keep away from all the hazards, rocks, right? So they're called hazardous cameras, but HazCams for short. And so actually one of the things that I got to work on when I first started at JPL was to support the fabrication of the HazCams, working on small components, qualifying them to get ready to fly on Mars, which is one of the coolest things that, at least for me, always wanting to work at JPL, I got a chance to do. And to me, when I started, I was still just mind blown that I was able to work there. And so, yeah, if you go to slide 13, these are the two other cameras that are similar to Curiosity rover. The Curiosity rover had the Mastcams, but these ones are going to be the Mastcam Z. So the Mastcam Z actually will be able to take longer range photos as well as panorama photos, and have a higher definition in imagery to give us a better feel and a better sight of the surface of Mars. So we actually will feel like we're there, and it's going to be super exciting. And then we have the SuperCam. The SuperCam is actually has a laser on there that will also be looking for organic chemicals and elements, but they'll actually be using the laser to shoot at rocks that the arm can't reach. So actually the arm is only rated to go up to about 7 feet out. And so there are going to be areas where the arm cannot reach, so we'll be using the SuperCam to get to those areas. Previously on the Curiosity rover, we had what was called the ChemCam, which is it was a similar concept, being able to look at organic compounds and use a laser to get to the areas that we weren't able to. But if you think about it, when we built the Curiosity rover, it was back in the early 2000s, and so, or it was it started in around 2003, 2004, and it didn't launch until 2011. So that technology, when we started building it, was from the early 2000s. But it's kind of the same thing with the Perseverance rover. When we started building it, it was in the early 2010s. So this new technology isn't really as new as we would like to, but it's something that we're going to be working with, and we're super excited to get the science back. So if you go to slide 14, slide 14 shows kind of like a rendition of what we'll be, like using the SuperCam for. Be zapping rocks about 20 feet away and being able to pick up those and study those rocks. Study the rocks for organic chemicals. So that's gonna be super exciting. And alongside with the cameras, if you go to slide 15, we're actually going to have 2 microphones on the rover to be able to listen to not only the winds of Mars, but also be able to listen to our instruments working on the surface of Mars. Previously, when we tested, for example, when we tested the SuperCam, when it zaps the rocks, it makes a loud like zapping noise. So being able to hear that on the surface is going to be incredible. And I'm sure all the people from the SuperCam team cannot wait to get there. And as well, so we also have another camera, or I guess a radar that we have on the butt of the rover. It's going to be, if you go to slide 18, this is called the RIMFAX. So the RIMFAX is going to be looking at the subsurface of Mars. So as we are roving through the surface, we'll be collecting data and seeing to see if there's any geological features under the surface that we can look at. And then we'll, this will also help us kind of understand more of Mars as we rove along without any interference of any of the other instruments. And then, so along with those cameras and microphones, we will also have, if you go to slide 19, we have a weather station called META. And this weather station will be taking the temperature, humidity, and the speed of the wind. And so we'll actually kind of be able to finally understand how the weather on Mars works. So, and if you go to slide 20, we can see this quick video of the Mars Perseverance robotic arm doing a bicep curl. And so one of the exciting things that I got to work on the MGSC side of the Perseverance rover was testing of the robotic, what we call the robotic arm mass model. So what that means is we took the exact same structure and the exact same weight of the robotic arm that we used on the flight model, but we use this on the what we call the development test model, which is the DTM unit of the Perseverance rover. So if you didn't know, we typically at JPL, we make two rovers, right? One's for flight and then one's for testing. There are other components to the other rovers that we do make, like the Scarecrow, but for the most part, we make 2. And the flight unit, obviously, we can't do all the testing that we'd like to, because if anything does happen to that rover, then we'd be screwed. But with the development test model, we are able to put that through the tests and to see if it would injure some of the testing that we do. So for the DTM rover, one of the tests that I was a part of was the centrifuge test, which we tested the entry of the Perseverance rover coming into the atmosphere of Mars. So with the centrifuge test, we rated this at I think it was about 13 to 15 Gs, whereas from the data that we collected from Curiosity, we're only rated to go at 9 Gs entering into the surface of Mars. So we bumped it up a little bit to see if our rover would withstand that force going into into the surface, which is a pretty incredible thing to be able to do without having tested the actual flight unit. But a lot of things go into testing, and we only get one shot, so we have to make sure that everything is done right and done correctly, and also rated more than we're supposed to. So just in case of anything, we can withstand that much more power, that much more strength. But the exciting thing that the most thing I'm excited for the Perseverance rover is actually the sample caching system. So the sample caching system is actually going to be what will be paving the way for future robotic exploration. So we actually have a system that will be collecting samples. So collecting the samples from the robotic arm putting it into the bit carousel, and then transferring the soil samples, and then kind of depositing them on the surface for a future Mars mission that we call the Mars Sample Return Mission. And if you go to slide 22, you can see the Mars, the sample caching system is right in front of the rover. So it's actually, if you think about it, we actually have 3 robots on Perseverance. One is the robotic arm. The second is the bit carousel that rotates the soil samples from a horizontal point to a vertical point, and then as well as the SHA, which the SHA is the sample handling arm at the bottom of the rover. So the SHA will pick up the samples that the robotic arm has put into it, and then it'll move it. And so we're actually going to have 43 sample tubes, 5 witness tubes, which the 5 witness tubes are preloaded with material that will help us detect any contaminants in the environment of which we collect those samples in. And so, so like during those witness samples, we'll be able to use those and deposit those along with the extra pile that we'll be depositing those samples in. And those witness tubes will help us see if there's anything that we've brought to the surface of Mars that's on the rover, anything, any contaminant, any chemicals, anything that the rover has deposited. And so if you go to slide 23, this shows the Mars sample kind of caching system, or the depot case that will hopefully be returning to Mars in a crazy mission that has collaborators such as the European Space Agency and others. So what we're going to be trying to do is take an orbiter, a lander, and a rover to pick these samples up and bring them back to Earth. And the reason why we're bringing them back to Earth is we can't take the best laboratories, the best chemists, the best scientists to Mars. So why not bring them to Earth, bring the samples to Earth so we can study those here. And so then we'll have the best scientists, the best laboratories working on these, and we'll be able to analyze those samples in a much closer and with higher rated machinery, so that we'll be able to actually see if there is signs of life. But then you might also be asking, like, how is this rover being powered? So just like the Curiosity rover, the Perseverance rover is powered by something I mentioned earlier, the MMRTG, which is at the end of the rover, which is rated to 110 watts. And this will help power the entire rover during its mission and give power to all the instruments that are on board. And also you might be asking something that we never really talk about, and I don't know if people have asked, but why is the rover painted white, right? So actually at JPL, we tend to paint our rovers whites to help with the thermal properties, and also keeping the rover warm inside, and also reflecting the sun back out. That's also one of the reasons why we don't have the wheels painted white, because there's no real need to. There's no instruments inside of the wheels, except for the motors, but the motors are already taken care of. So if you go to slide 26, we can see the entry, descent, and landing phase. So for the new rover, we actually have terrain relative navigation system that will help the rover get to the area that it needs to safely. So we have a new technology, and along with the cameras on board, that will be taking snapshots of the terrain as it's lowered onto the surface of Mars. Unlike before, the Curiosity rover did not have this technology. So Jezero crater is actually known as a hazardous area, which we weren't able to land before. But now with this technology, we actually are. And so that's one of the new cool instruments and new technology that we're actually able to implement this time around. So kind of like something I've been kind of talking about is the technology keeps advancing. So as we get further and further along, we'll be able to make new technology and use it for future Mars exploration missions, which is really exciting because the Mars sample return is actually, I think there's no exact date, but it's supposed to launch sometime around 2026 and hopefully return those samples in 2030s. But it's still kind of up in the air and it's still in the campaign phase. I guess we can take a look at slide 33, which will be this. So we'll be communicating with the Mars Perseverance rover through a deep space network. And so what this allows us to do is communicate with our orbiters. So we have a few orbiters on Mars. Actually, one is from the European Space Agency, and the other one is the Mars Reconnaissance Orbiter, which is the MRO. And so we'll be able to communicate with those orbiters once Perseverance lands. It'll connect and communicate with the orbiters, and from the orbiters, we'll relay that message over to us. But one of the most challenging things is, communicating with our rovers on Mars. It takes about a 14-minute, relay delay going from there and then back to Mars, or there and then back to Earth. Hopefully, when we do kind of advance more of the technology, we'll be able to communicate a little bit faster and better. And actually, one of the new programs that I'm a part of is called DSOC, which is a Deep Space Optical Communications, which will be hopefully improving the communication between Earth and deep space, which is also really exciting to see and to kind of be a part of at JPL. So one of the last things I kind of want to talk about before I miss it, and we're kind of like running short on time, is the Mars helicopter. So if you go to slide 35, the coolest thing, the cherry on top to this whole Perseverance mission is that won't really interfere with the actual objectives of Perseverance is the Mars helicopter, which is Ingenuity. So the Mars helicopter will be deployed a few months after landing on Mars, and as soon as Perseverance is about I think 100 meters away, the helicopter will be able to start flying, and hopefully we'll be able to get some data back to see how a copter kind of can fly on Mars with such a low density of atmosphere, which is 1% that of Earth's. And so the helicopter will actually be flying for 90 seconds at a time, and it is about the wings are about 4 feet, has 2 blades, and it's supposed to spin about 2,400 RPM. And so this 4-pound copter will be the first powered flight on another planet, and that's really, really exciting to see. Because this isn't interfering at all with the Mars Perseverance rover. It's actually adding to the mission, being able to use the 2 cameras on the copter to be able to see further than the rover can see. So this is really exciting, and all this is happening on February 18th, 2021. As soon as we land. It's going to be such an amazing feeling and moments, and it's going to be a time in history that we'll be able to look back at and say that, wow, we built this, we helped make this. But it's not just us at JPL. Everybody around the world is kind of all part of this entire mission. And for future missions to come out of this, we can't wait to see what science is and what comes out of this entire mission. So if you go to slide, I guess 38, if you guys want to go to mars.nasa.gov/Mars2020, this is where you can find more information on the Mars Perseverance rover, or if you just want to look at more information just about Mars in general, you can go to nasa.gov/Mars. And that's it for me. Thanks for everybody.
Awesome. Really appreciate this. I mean, so many things to like dig deeper in, right? I mean, this is just a highlight reel for so many, real interesting topics for us to kind of dig further into. Just some quick notes. I really appreciate you talking about Mars sample return. I know that that's still, conceptual at this point, but I feel like in the last couple of years we've seen all this talk of let's go to Mars, let's send people to Mars. But JPL is taking a little bit more of this. Why send people when you can send robots and bring Mars back to us? And I think that just makes so much sense. Another thing I thought was really interesting that you highlighted is this idea of subtractive engineering. I think a lot of people don't understand that you don't go to a hardware store and pick up the parts for a rover, right? These
Right.
need to be made in-house. I have a small little desktop model of the Perseverance, and it's a 1/10 scale, but I kind of can't grasp how big this truly is. So I also have actually a wheel. So this is what Leonard makes, right?
Yeah.
So to kind of get a feel for the scale of this thing, it's really pretty wild. So we have a ton of questions, some really good questions to kind of go through. The first one is if you can comment a little bit about how much of the campaign for Perseverance is already planned out. What's the level of flexibility, or is this kind of already mapped out to the day?
Yeah, so the Perseverance campaign is actually it is mapped out in a way where right now there are folks doing like surface operations where they're getting ready to do all the science that is required of the Perseverance rover once they land on Mars. However, once we land on Mars, there's going to be some flexibility of what actually needs to happen, and if there are any issues with some of the instruments, then that kind of takes a planning, right? So there's always going to be planning along the way, and as well as to make sure first that all the instruments are actually working and alive. First we have to see how the Perseverance rover is operating and see if all the instruments are well and alive and to be able to do their operations. But for the most part, there are a lot of engineers already working on their schedule, and as soon as the rover lands, at least as soon as we get closer to the landing date, we'll have a better idea of the actual planning behind these operations. But again, sometimes things don't go as planned, and as we all know, we're humans, so we adapt to the situation. So we will be able to adapt to whatever comes our way and figure it out. As engineers, we like to solve problems. That's what we'll be doing.
Yeah, I think it's a Mike Tyson quote, says everyone has a plan until they get punched in the face, right? You gotta get there and reevaluate and see how we're doing.
Hopefully we don't get punched in the face.
Several questions from Maryhill Elementary. They're kind of asking about Jezero Crater in particular. We're there because we thought water was once there. Are there signs of water on Mars already? Do we know that it's there?
So there are, but right now we are looking at the polar caps. So there's ice beneath the surface, or also some on the surface, but it tends to evaporate rather quickly. So seeing that there is ice, we kind of concluded to that being water, but there's not actually flowing water. So that's one of the reasons why we also want to investigate the subsurface to be able to see what is underneath Jezero Crater, right? To be able to go towards that area and kind of get the sediment of rocks and see if there is life. But there has been some research that has been done and some analysis that there once was water flowing. So we believe, and we are going to the sciences to go there and to figure out once and for all if there is life and if there was once water.
Yeah, that kind of leads well into another great question Cristobal asked, which is, here you are, a manufacturing engineer, asking and answering questions about, the scientific instruments, about the geology on Mars. It seems like JPLers have this wild, broad knowledge, right? I mean, this is certainly beyond your original skill set. So can you comment a little bit about how it is that you, in your role, communicate with other disciplines at NASA and JPL?
Yeah, so my role, as a manufacturing engineer, we kind of deal with the mechanical and physical hardware of things, right? But I would say kind of like through my curiosity and through, I mean, because it's kind of how you said, JPLers tend to kind of open the spectrum and to broaden their knowledge of things, is because I believe we're all curious and we all like to kind of know a little bit of everything, and kind of our minds go to where we find interest in, right? So at least for me, I found interest in Mars kind of at an earlier age. Before JPL, I was actually a part of another rover team during my undergrad. So I was part of the Titan rover. So that was kind of my first introduction into getting then diving into what Mars is about. So over time, just kind of me being curious and always wanted to know everything, and obviously, and also be challenged on how to even get to Mars and do science there. It kind of opened my mind to be able to, or to want to know these things. So now it's kind of outside of my role, but it's also something that I've always just kind of liked to do and learn and know.
Yeah, and in a similar vein, do you have advice for kind of young students? We have several, engineers to be on the stream right now, and they're asking questions like, what do we need to pursue? How can we be part of this pretty exciting future of Mars exploration? So, any kind of career tips or how you got to where you are?
Yeah, so to be, part of the, I guess I would say this Mars Exploration Society, you don't necessarily need to be an engineer. I know a lot of folks who aren't engineers, but are also part of this whole endeavor. Kind of like Brandon, like you yourself, you're from the educational office, and you're in the space industry, the space program. So it's kind of my take would be, just follow your passion, follow your dreams. That's kind of what I did. I didn't really start by like looking up this, like looking up at the stars, like most people have this story of like, hey, I was a little kid, I was looking up the stars, and now I'm here at JPL. Actually, mine started off like a little later, but I did have an interest in engineering. Kind of a funny story is my dad, he was a bodybuilder when he lived in Mexico. And so he had, one of his idols was Arnold Schwarzenegger. And so when I was at a young age, I watched The Terminator. And so the first scene that I saw that skeletal hand move, and I saw all the intricate, mechanisms working there, that kind of sparked my curiosity and trying to understand how is that working? Like, why are these AI robots able to move and function? So that was my first interest in engineering per se. But then later on, once I graduated college, or sorry, once I graduated high school, I actually that's when I first heard of and saw the Curiosity rover launching. And when it landed and I saw that 7 minutes of terror video, that was the moment that kind of led me into the path to working at JPL. After seeing that 7 minutes of terror video, it made me want to challenge myself and to see, like one of the things I always ask myself, like, what is the most hardest thing to do? Like, what's the most challenging thing? And I think space exploration is definitely up there. And so, I like to challenge myself. And so what I did, I just, kind of stuck to my guns and started down the path to trying to work at JPL. And eventually, over time, I did a couple internships, not at JPL, but other places, trying to get experience. I worked full time, not in the space industry, and it wasn't until 2018 that I actually got picked up by JPL. But just over time, I just kept applying. I kept persevering through, and eventually, like my passion, my goal, kind of shown, like it kind of showed through. during my interviews, and yeah, and now I'm here at JPL. It's so the biggest key takeaway I would say is just follow your dreams, follow your passion, and just keep on going, keep tackling at it, and persevere.
Yeah, that's, I mean, incredible to hear, because I think a lot of people don't understand how diverse the skill set is at NASA, not just within science, but as an organization that's so public facing, we need the best writers, we need the best web designers, we need so many different skill sets to be able to communicate what it is that you do with the public. And then I also noticed that I think everyone here heard it first, that if Skynet goes active, we have Leonard to blame. That he very motivated by the destruction of humanity.
Yeah.
Another question that this is a tough one, but maybe you can comment at least on the process. Do you know of any instruments that were kind of hopeful to make it on the Perseverance rover, but maybe got cut due to cost or weight? And if not, then just, what does that evaluation process look like?
Ooh, that's actually a really good question. I actually don't know which ones got cut, but I know some of these instruments have been kind of talked about for a long time, trying to get onto the Perseverance rover and previous rovers as well. I know the sample caching system, at least for the Mars Sample Return campaign, has been decades worth of work. But as far as the ones that have been cut, I'm not really sure. But there is a process that that a lot of some agencies and companies do try to kind of negotiate to get onto the Perseverance rover. If you did not know, some of the instruments aren't all from JPL, from the US. We test and assemble them here, but we don't necessarily build all of them. There is a few that are from France and Spain. So the Perseverance is actually a collaboration between a lot of countries and a lot of people, a lot of scientists. So that's also why another reason why like what makes Perseverance such a good rover, because it's not just for the U.S. to kind of flagship on this, but also the entire world. It's not, the science isn't going to be just for us. It's going to be for everybody to know and understand.
I have one last question for you before we go and switch to some talk on the education side. There are some rumors here about some sort of Morse code imprinting on Mars. Can you kind of explain that folklore and that tale?
The Morse code. Are you talking about the Curiosity rover or the Perseverance? There is some on the Perseverance as well. So the Curiosity rover, essentially, the engineers that were working on the wheel at one point wanted to put the letters JPL onto the wheel without kind of getting NASA's approval. And so what happened is they didn't get the approval, so then they put what's Morse code for JPL, but they put these imprints into the Curiosity wheel, and their explanation was this will help us kind of measure and track the distance from which the Curiosity rover is traveling. Little did the folks at NASA know that these imprints are actually Morse code for JPL. And so that's kind of the folklore of getting things onto the rover without people knowing. And there's actually a couple of things on, one mainly on Perseverance. Actually, the emblem of the Mars, Sun, Earth next to I believe the 10 million people that signed up to go get their name sent to Mars. So it's right there on the emblem. Not really sure. I forget exactly what it stands for, but yeah, JPLers tend to sneak in things onto the Perseverance rover. It kind of makes it a little fun for everybody, not just for us, but people down the line to talk about things like this.
Yeah, it's definitely my favorite story of all of the crazy JPL antics. Just coming in and working here just showed me these are the bad boys and girls of nerd stars. So.
Yeah, I mean, essentially, we're all kind of just kids working in like a hobby shop. I would say, kind of tinkering with tools and toys and seeing what works, what doesn't work. But ultimately, trying to create science and instruments that will actually pave the way for future, exploration and things to get that data and science back. But in the end, yeah, I feel like we're just all kids, and it's really, really fun to be part of JPL. It's like it's like a dream come true to be able to just tinker with things, and yeah, you just feel like a kid at a toy store.
Well, thank you so much for taking the time today. We really, really appreciate it. Always interesting to hear just how crazy and novel and how collaborative all of these projects are, all on one rover. So hopefully that gives our viewers something to kind of look forward to and look into a little bit more. So I thank you so much for your time. We'll definitely chat soon, and really appreciate you joining us today.
Great. Thanks for having me.
So we'll close out the rest of the call just by looking at a little bit about some of the educational resources that you can utilize to take what you heard Leonard talk about today, again, to your home, to your classroom, or if you're just passionate about science. So what you'll see here on this first slide is kind of the landing spot for the JPL education page. At the top, you'll see some options for ways for you to explore. Some of them more educator focused, some of them for the just science enthusiasts. Maybe the events section that you see at the top is how you found this session today. So that'll give you a little lineup of what we're doing and where we are. On the second slide, you'll see that we have tons and tons of activities that tie directly to the type of science and engineering you heard Leonard discuss. Marsbound, for example, is a lesson where you design a Mars mission on your own. So now that Perseverance is on its way, what will the next one look like? How are you going to power it? What science is it going to do? And this is a really great engineering kind of concept building activity. So, by the time an idea gets to manufacturing, there's already been discussion. We don't go into the workshop and start building. We got to know our goals, we got to know our plan, we got to know our blueprint, and that kind of models that in Marsbound. On slide 3, you'll see a little bit more of activities pertaining to, for example, Mars sample return. So this is modeling the coring sample and caching for this future mission. Again, all grade levels being represented, explanation for how this ties in, and then resources for your future reading as well. If you are an educator, you'll see on slide 4 that what we try to do in the education department is put these together a little bit for you as well into like a narrative. So instead of just having one-off lessons, what if there were 6 or 7 lessons in a row that you could do, such as a mission to Mars unit. So instead of just landing or just doing science or just building, what does it really take to get from start to finish? On slide 5, you'll see some examples of the kind of news that's coming out of the education department. Again, written for students, for the casual scientific observer. And this is a good chance for you, if you're not a classroom educator, just to stay up to speed. It's overwhelming, I'll tell you. Leonard did a great job answering some of these questions today, but you got to think it takes a lot of work to kind of, not just stay too deep in your tunnel vision on your one topic and being able to understand all of the process around you. And this is just Mars, by the way. We haven't even talked about the rest of the solar system or beyond that. So staying up to speed can be tough, but this will give you a chance to kind of read about it and really just stay excited about all the cool things happening in space science. On slide 6, my teacher types will enjoy going to this teach section. This is written for you guys. This is lesson plans, activities, all already in a 5E model if you're a 5E kind of person. I know I am. And worksheets are made, answer keys are already prepared, class management tips. The idea is that my team is all ex-educators. We've all taught in the classroom, so we know exactly what it is that you guys need. And the answer isn't thick binders full of things for you to go do. So instead, what can you just take off the shelf and hit the ground running? Because times are what they are, on slide 7, you'll see in the learn section that if you are in like a distance learning or remote learning environment, these are activities that are written with a little bit more of a student focus. So if you are, want to assign something, or again, if you're just, excited about science and want to try these at home, these are written in a more stepwise format, pictures and directions, so that you can do some of this cool research at home. You'll see drop-down menus throughout to allow you guys to kind of pick, what grade level is my kid or my students, so that you can kind of get it to represent the right difficulty level. On slide 8, you'll see how we've kind of compiled that into what we call learning space. And this is, again, all of these kind of features in one place. Activities, we're filming video tutorials so that you can watch us kind of run through some of the sample lessons. We're translating everything into Spanish as well, in case you are a Spanish speaker or have Spanish speaking students. And then just FAQ for families as well. So tons and tons of resources here for you, for your family, for your students. And then lastly, on slide 9, again, this is just a brief introduction to the resources at JPL. Please dig deep into this website. I know you're going to love it, no matter your background. And then recall that, as I mentioned at the top of the hour, one of the things that we're really excited about doing is, again, having kind of a follow-up session. So on the Saturday after today, we will, this is posted on the events webpage as well. We have registration for a teacher audience in particular to take what it is that we discussed today and then kind of implement it in a classroom. So we'll actually model some of these lessons. We'll dig a little bit deeper, and that should give you guys some more context and opportunity to play with what it is you're hoping to share with your kids. So with that, I'll kind of close out. I thank you guys so much for joining us again today. I hope you enjoyed this series. Yeah, we will always post these. So if you have a friend or a colleague that missed, there'll be the recording will be posted on the education website as well as on YouTube. And we'll do this again next month. You actually heard Leonard talk a little bit about DSOC, advancing how it is we communicate with spacecraft. And coincidentally, that'll be our topic for next month. So how is it that we communicate with spacecraft literally hundreds of millions of miles away? How are we transmitting data that's getting bigger and bigger, these 20 megapixel cameras? How do you get these beautiful images back when you're at such a great distance? So we'll explore that a little bit as well. So I hope you enjoyed today. I hope to see you next month. And thank you so much for joining us. Have a great day.